One of the less examined logistical challenges during the war was not strategic movement or battlefield coordination, but actually the performance of materials under environmental stress. Timber used in bunkers, temporary bridges, and supply structures frequently failed in ways that were not caused by combat. It warped under humidity, fractured under freeze-thaw cycles, and honestly degraded faster than projected lifespan estimates. Engineers working in the field often found themselves maintaining structures that were theoretically sound but materially unstable. This gap between expectation and performance highlights a recurring issue in 20th century logistics, the assumption that industrial production could substitute for long-term environmental conditioning. That assumption becomes more revealing when examined alongside earlier construction systems that operated under far more limited technological conditions. Medieval builders, lacking synthetic sealants and modern chemical treatments, developed wood preservation techniques that in many cases produced longer-lasting results than some contemporary methods. These were not isolated innovations. They were integrated systems of material preparation, environmental control, and structural design. Medieval builders understood that wood begins to degrade long before visible decay appears. The foundation of medieval wood treatment was not chemistry in the modern sense, but observation of material behavior over time. Builders recognized that once a tree was felled, it entered a transitional state in which moisture redistribution, microbial activity, and structural tension continued to evolve. If unmanaged, these processes led to internal instability that later manifested as rot or deformation. This understanding shaped the earliest stage of material selection. Timber was often harvested during colder months when sap levels were low. Reduced sap content meant fewer nutrients available for fungi and insects, slowing early-stage decay. It also reduced internal moisture, which minimized the risk of uneven drying during later processing stages. Selection also extended to tree characteristics. Slow-grown timber, particularly from harsher climates, was preferred due to its tighter grain structure. This density reduced permeability and increased resistance to cracking under environmental stress. These choices were based on repeated empirical outcomes rather than theoretical models. Once harvested, wood entered a controlled stabilization process that determined its long-term performance. Fresh timber was not used immediately. Instead, it underwent a seasoning phase designed to stabilize internal moisture levels. The objective was not simply drying, but achieving equilibrium within the material. Uneven moisture loss creates internal stress, which eventually leads to structural failure, even in otherwise sound wood. Seasoning methods varied, but the underlying principle was consistent. Timber was stacked in configurations that allowed airflow while protecting it from direct rain and ground moisture. Elevation was commonly used to prevent damp absorption from soil contact. Spacing between beams ensured that air circulation reduced localized drying differences. This phase could last months or even years depending on intended application. Structural elements required longer stabilization periods than non-load-bearing components. The time investment reflected an understanding that premature use of timber reduced its eventual lifespan significantly. The effectiveness of medieval preservation depended on modifying how wood interacted with its environment. One of the most widely used preservation substances in medieval Europe was tar, produced through controlled thermal decomposition of pine wood in low oxygen conditions. This material was not applied as a surface coating alone. It was worked into the grain structure, allowing deep penetration into outer layers. The function of tar was not to create an impermeable barrier. Instead, it altered the material's interaction with moisture and biological agents. By reducing permeability while maintaining flexibility, it allowed wood to respond to environmental changes without fracturing. This balance was essential in regions where temperature and humidity fluctuated significantly across seasons. Other treatments complemented this system. Oils derived from animal fats or plant sources were used to condition fibers and slow moisture absorption. Lime-based coatings, particularly in northern regions, provided an alkaline surface environment that inhibited microbial growth. These treatments were not interchangeable but part of a layered approach to material stabilization. Structural design played an equally important role in long-term wood preservation. Material treatment alone was insufficient without architectural adaptation. Medieval builders incorporated environmental management into structural design itself. Roofs were extended beyond wall lines to direct rainfall away from timber surfaces, reducing prolonged moisture exposure. Foundations were frequently raised or constructed using stone bases to isolate wood from constant ground humidity. This prevented one of the most common pathways for rot initiation. Even simple elevation changes in building placement reflected an understanding of water movement across terrain. Drainage systems, even in rudimentary forms, were essential. Water accumulation around structures significantly accelerated decay, and settlements were often planned with attention to natural runoff patterns. This integration of environmental awareness into construction design contributed significantly to structural longevity. Joinery techniques also supported durability. Flexible joints, such as mortise and tenon, allowed slight movement within the structure without compromising integrity. This reduced stress concentrations caused by seasonal expansion and contraction, which are major contributors to long-term material fatigue. Maintenance was not an auxiliary practice, but a core component of medieval construction systems. Unlike modern approaches that often assume minimal intervention after completion, medieval timber structures were designed with continuous maintenance in mind. Individual components could be replaced without dismantling entire buildings, allowing for localized repair rather than systemic reconstruction. This modularity extended functional lifespans significantly. Structures were not static entities, but evolving systems. Early signs of decay were addressed as part of routine upkeep rather than emergency repair. This approach required familiarity with how wood changes over time under environmental exposure. Maintenance practices reflected a broader philosophy. Durability was not achieved at the moment of construction, but sustained through ongoing engagement with material conditions. When compared with 20th century military logistics, the differences in material philosophy become more apparent. During the Korean War, rapid construction requirements often prioritized speed and scalability over long-term environmental conditioning. Timber was processed and deployed within compressed time frames that limited natural stabilization processes. While this enabled large-scale infrastructure development, it also reduced material resilience under extreme climatic conditions. In environments characterized by humidity fluctuations and freezing temperatures, insufficiently conditioned wood exhibited predictable degradation patterns. Structural deformation, joint loosening, and surface decay increased maintenance demands throughout operational use. These issues did not determine strategic outcomes but influenced operational efficiency and resource allocation. The contrast does not imply technological regression in modern systems, but rather a shift in priorities. Medieval systems were optimized for longevity under scarcity. Modern systems are optimized for rapid deployment under logistical abundance. Each reflects its operational constraints. The underlying principle is that material longevity emerges from system integration rather than isolated treatment. The so-called medieval wood treatment that appears to outperform modern sealants is not a single technique but a coordinated system. It combines material selection, controlled drying, chemical modification, architectural adaptation, and sustained maintenance. Each component reinforces the others. Removing one weakens the entire system. This interconnectedness is critical to understanding why these methods achieved long-term durability without synthetic chemistry. Modern materials science has expanded the range of available treatments, but the fundamental challenge remains unchanged. Wood is a responsive material. It reacts continuously to moisture, temperature, biological activity, and mechanical stress. Effective preservation must account for all these variables simultaneously. What medieval practices ultimately demonstrate is a disciplined engagement with environmental limits rather than an attempt to eliminate them. Medieval builders did not aim to make wood permanent in an absolute sense. They aimed to control the rate and pattern of its deterioration. This distinction is central. It reflects an understanding that all organic materials exist within cycles of change. The durability achieved through these methods was not the result of hidden knowledge or lost technology, but of consistent observation and structured practice. Over time, these practices produced systems that remained functional across generations. In survival contexts, construction planning, and material science, this perspective remains relevant. It emphasizes that longevity is achieved not through resistance to environment, but through alignment with it. Understanding these systems provides more than historical insight. It offers a framework for thinking about durability in any context where materials are exposed to time and environmental variation. If these deeper historical systems are worth exploring further, subscribe to History Vault and share this video.